We'd like to discuss the airflow in pipes experiment. Now, the objective of this is going to be, we want to be looking at the energy loss. And you might remember from class, we talked, or from the lecture class, Engineering 115, we talked about major and minor losses, or what we also call friction loss or local losses. And so we want to quantify the change in pressure along the pipe and determine that loss in pressure that exists due to different components, all right, and friction. Right? In addition to that, we're going to be looking at the velocity profile at the exit plane, and we want to see that parabolic, or I shouldn't say, we're probably going to see a turbulent flow, so we should see a 1/7 power law. And you might recall if it were laminar, which it probably won't be, you would get a parabolic flow profile. But what I wanted to highlight there is the maximum velocity in the center of the pipe, where it transitions somehow to zero velocity from the no-slip condition at the wall. And then lastly, there's an orifice meter inside the system, which we want to try and quantify its discharge coefficient. Right? All right, so the first thing to do then is to take a look at what an image of this experiment looks like. You'll see this along the north wall of the lab. We have a centrifugal fan, and that's going to be pushing air through this pipe and out the top here at the exit plane. Now, you'll see that all of these letters, A through L, are little static taps, all right? And here I have a zoom in on what they look like, a wall static pressure tap. There's a little valve here, and if you make this little handle go parallel to this pipe, it'll open the valve, and that will allow flow to come out of this pipe here. And what we're going to do is we're going to take a pressure sensor and some tubing, connect it to this barb fitting at the end of the tap, and that's going to allow the pressure to be transmitted through that piping or soft tubing to the sensor to measure the static pressure. Okay, now since the flow is going horizontally here and the hole is at the top and this pipe is perpendicular, you might remember that what we'd be sensing is the static pressure. Okay, so each one of these letters, there's a static pressure tap where we can get the local static pressure. And what we should see is, for the majority of this, there's one place where this is not true between B, C, and D, where the orifice meter is placed. But what we should see is the fan producing a high pressure and that dropping lower and lower and lower until it finally hits zero pressure condition at the exit plane here. You might recall zero gauge pressure exists at an exit plane from what we call the free jet. Okay. Now, in addition to measuring the static pressures along the length here, we're also going to be using a pedostatic tube to measure the velocity at the exit plane. We're going to place the probe at the center of the pipe, and then we're going to traverse it to one of the walls. Currently, this has been modified slightly where the probe is vertical, and so you're going to start the probe in the middle and then move vertically upward to the inner wall of the pipe. So here is a slide that shows, let's look at the right here. The right shows R over capital R, which is the non-dimensional radial position. So capital R is the actual radius of a pipe, and little r is the local position radially. So when that ratio is 0, you're at the center of the pipe. When that ratio is 1, you're at the wall of the pipe. And you can see in laminar, that was the quasi-flow, if you might recall from lecture class. We got a parabolic flow profile, okay? And if the flow were turbulent, there was no analytical solution. But what we saw is that because of the mixing that exists, because of the turbulent eddies, you have a much more uniform speed throughout the majority or the center of the pipe. See how this is staying relatively constant for a while. And then there's a sharp gradient at the wall. That sharp gradient at the wall gives us high shear stresses and high losses in pressure that exist. All right, but you see in all of these cases, we go to 0 speed at the wall, which is the no-slip condition. All right, now the actual curve here is a function of this parameter n, all right, which is the which goes like the power. So we saw the 1/7 power law. So if n were 7, that would be the 1/7 law. And here, the value of n should be a function, or is a function, of the Reynolds number. Now, in general, we just typically use the 1/7 condition to be a good rough estimate. Right? Now, how do we actually calculate the flow rate in this lab? Here, what we're taking a look at is the exit plane. Okay, so here's the pipe diameter, and that little blue dot represents the center of the pipe. And imagine the flow coming out of the page. So that blue dot is going to be where we're first going to position the pedostatic tube, which is again an instrument that allows us to measure velocity. Right? So we're going to have the velocity at each position, the center, and we're going to move it or traverse it 2 millimeters across until we get, oh, excuse me, that point went a little too far, until we get to the outer wall. Now, how it's going to work is we are going to get the flow rate by discretizing the area, meaning we're going to first take a data point right in the center, and we're going to say that since we don't have an infinite number of points, that velocity is constant over some small area. Okay, and that area is going to be estimated first as this circular area that we see here. So you might remember that the flow rate is velocity times area. So initially, we're going to say that there's a contribution of the flow in this inner circle here, which is the velocity at the center times the area of this circle. And so you see here we have velocity at the center line, that's what the CL stands for, times the area of this circle. And the area is, of course, just pi r squared. So pi times the radius of that center line circle squared. Okay, so that gives me the flow rate in this little circular region here, or an estimate of that flow rate. Now, when I move the probe over 2 millimeters, now I can assume that we have an axisymmetric case, meaning the velocity is constant anywhere along this annular space. Oh, excuse me. And so now we're going to say that the flow rate is going to be the velocity times the area, but the area is now an annulus, okay? And so the flow rate then is going to be velocity. Here you see the velocity, Vj, which is the local velocity here, times the annular area, which can be calculated by 2 pi times rj, which is this local radius, times delta r, which is always going to be the 2 millimeters that we're moving. Okay? Now, we're going to then do the next one. Well, the next one is going to be the same formula. That's why we have a summation here. It's going to be the local velocity we measure here times 2 pi now rj times, again, delta r being 2 millimeters. And we're going to keep doing that until we get to one special case, which is the last point, right? So if I had one more point right at the end here, now, because the probe has some thickness, I can't actually get to the wall. And so I know the no-slip boundary condition would mean that exactly at the wall, I should have 0 speed, or let's just write 0 meters per second here. But I'll never measure that because I can never get exactly to the wall with my sensor. And so because of that, I'm going to put a little fudge factor here. I'm going to say, well, whatever I measure, it's kind of a bad average, or it's going to be a higher average because I know it drops to 0. So to put a little fudge factor on it, I'm going to multiply it by 2/3 because I know that value is a little bit high. So that reduces it a little bit. And then I'm going to multiply it again by the annular space in this region, which is going to be 2 pi times the outer radius times the delta r outer, which here this gap is not the 2 millimeters again because of the thickness of the probe, okay? And you can refer to the lab manual to give you what that delta outer is. Right? Now, when we want to study the losses, we have to remember there are two types. We have major losses, which is due to friction. And you might recall from class that we were able to measure the friction head by some friction factor times the length to diameter ratio times the velocity head, which we said was v squared over 2 times g. And this friction factor was the Darcy friction factor. And for turbulent flow, which is most likely what we're going to have, you get that Darcy friction factor by looking up the Moody diagram. Which, in order to use it, the friction factor is a function of both the Reynolds number and the relative roughness, okay? So in the lab manual, it'll tell you what material the pipe is, and you can use that information to go to tables, which will let you know what the roughness is, divide that by the diameter to get the relative roughness. And again, you can calculate your Reynolds number, which is like a non-dimensional velocity, okay? So we'll see that. I think I have an image of the Moody diagram right here. So you might recall, again, this table 8.1 has the estimates on what the roughness would be based on the material. Knowing that, you can calculate epsilon divided by the diameter, or relative roughness. And to use this chart, let's just give an example. If you had a Reynolds number of 1 × 10⁶ and a roughness of 0.006, what you can do, let me just highlight this line here for us. Find where your Reynolds number hits that roughness line, and then you can read straight across, okay? And you would be able to then see that you'd have a friction factor that was approximately, this looks like 0.018, right? So that would be an approximation of my Darcy friction factor. All right, and then again, we can use that to calculate what the major head loss is. Now, the minor losses, you might recall, are from components. And H sub m is the symbol we typically give that. And this is calculated by something called the loss coefficient multiplied by the velocity head v² over 2g, where this loss coefficient depends on the component itself, right, which is typically experimentally determined. And so we're going to be able to try and experimentally gain this, and we're going to compare it to tables that you might find in textbooks or produced by ASHRAE, which is the professional society that looks at heating, ventilating, and air conditioning systems, which often do these types of calculations. All right, but the idea here is anytime you have flow not just going in a straight line or down a tube, it's going to take some energy to like make a turn or go through a valve, and so that energy manifests itself in a pressure loss, and of course overall as an energy change. And so this could be due to, as you see here, flow going from some tank into a pipe, which we call an entrance loss, right? And the amount of loss is going to change exactly on how the flow is guided in. You see here, if the pipe is sticking in, the flow has a separation right on the leading edges here. You get these swirling flows, this detached region in here. That's going to waste energy because flow is just kind of swirling there. And so it's not utilizing the energy to just propel itself forward. So we're going to get a higher loss than if we put a nice radius on the system here, which is able to guide the flow in and reduce those separation zones, right? And ultimately give you higher values of performance, all right? Right. In addition to having entrance effects, you could have exit effects. Again, it's really dependent on how well you guide the flow through. This would be high levels of loss. If it's guided out, it should get much lower, right? But it's all based on the geometry itself. And so you'd see tables like this that are calculated from other people's experiments, which allow you to get estimates on what your loss coefficient is dependent on the area ratios. Okay, so you'll find out what you have. You can measure what those ratios are and allow you to come up with an estimate of the loss coefficient, and you'll compare that to the experimental data that you collected, right? Well, again, in your exit, or if you have an expansion section, the area ratio is going to affect what that loss coefficient is. We'll also have losses from flow going around elbows, right? So here again, you can see depending on what the radius of curvature is, right, how drastic it is, you might get some flow separation, which brings about energy loss. In addition, as flow goes around a turn like that, there's a radial pressure gradient in addition to the pressure gradient along the pipe length, which actually produces what we call secondary flow structures, or these two counter-rotating flows, where that's going to bring about more loss because again, it takes energy to have the flow move in these circles as opposed to just going forward or through the pipe. All right, so depending on what your relative roughness is and what the radius of curvature is, that will allow you to determine what the loss coefficient would be. Okay. We stated earlier that our system has a orifice meter. So you might recall that an orifice meter is what we call a Bernoulli type device, which allows us to measure flow rate. That's the idea behind it. Now, in order to measure flow rate, you have to know what its discharge coefficient is. So in the lab, we're going to know what the flow rate is by traversing that pedostatic probe at the exit plane of the pipe, which I mentioned earlier. And since we then know what the flow rate is, we can back calculate what the discharge coefficient is if we simply measure the pressure before and after the orifice, where the orifice is simply like a flat plate stuck in the pipe with a hole drilled out the middle. So all of the flow gets forced into this smaller diameter, right? You might recall that smaller diameter means higher velocity. Higher velocity means lower pressure. So the change in pressure here, the delta P across these 2 points, can be related back to flow rate through the discharge coefficient, which quantifies the change in energy due to the vena contracta, which is the fact that the pressure is going to be dependent on the local speed, which is based on the local area, which happens to be slightly smaller than the diameter of the hole itself. So as the flow goes through that small orifice hole, it actually necks down a little bit more, meaning we'd get functionally higher velocities, right? And that's the vena contracta. In addition, we have some energy loss due to the flow separating here and swirling backwards. So those losses are the reason for a discharge coefficient in our formula.